Recording is rolling. It is Wednesday, October 16th. I have a couple water demo for you guys I'm going to do here pretty soon. It's going to lead into the Centripetal Force Lab. You guys have, well, this lab page from last few days with the turntable. You flip it over on the other side, there's a table for, hey, Centripetal Force Lab. There's a bunch of spaces for graphs. The graphs we're going to save for Friday. So today, go ahead and collect your data. AP, right now, you guys in front of me right now are not AP, but here, okay, I have a poster just for my AP students. So since I'm doing a recording for everybody, if you are AP, then how do you do an AP style write-up? And we're going to score that a couple of days. Right, but all my other classes, don't worry about that one so much. All right, so we got tomorrow, guys. Tomorrow, where are you going to meet me? Where are you guys going tomorrow? Media Center. Media Center. Right. Unless, of course, you're in 10th grade, you might be taking the PSAT, go wherever you're supposed to go. But if you're past that, to go to the Media Center. I'll meet you guys in the Media Center. Got activity there. Right. Then Friday, we'll be back in the classroom. We'll be finishing this lab on Friday. So gather all your data today. And then on Friday, we're going to put the graphs together. Like you might be able to do a couple graphs on your own, but not all the graphs because there's multiple parts to this lab. Okay? I need to split you guys into different teams and each doing a little bit different experiment. Okay. All right, so you guys good so far? What we're doing? Okay. Oh, also got a note here at the bottom. ASVAB. There's a test next week called the ASVAB. If you're in 11th grade, you're almost certainly taking it, which is almost everybody. So I did get an Excel file that has testing locations. I cleaned it up a little bit, so it just has your name and where you're testing. That is on. Guess where that's posted. Guess where you can find that? Google Classroom.
Is there a movies with contact if we were not going to be able to show the because I have a field trip on that.
Oh, can you talk to maybe guidance maybe? Or yeah, you have field trip. Yeah, maybe I'll send you guidance later. Yeah. All right. So you guys good with everything going on so far? All right. And so let's go back to the top here. A cup of water demo. All right. So I have a cup right now. It's empty, but not for long. So some water in here. Now this is half full of water. You guys see it? Half full of water? You see that? Half full of water cup. Hey, how can I turn this cup of water upside down and not get my floor all wet? Yeah, if I spin this in a vertical circle. Okay, so if you're watching this video later, just imagine I'm spinning this in a vertical circle. Hey, look at that. The water's not falling out of the cup. Look at that. What if I do a little slower? What if I do a little slower? A little slower. Do you think at some point it's going to be too slow and the water actually will fall out? Right. There's the water's still in the cup, so it's all right. But yeah, hey, I wonder what is the minimum speed to get around. Now, we're not going to answer that question today, but you guys got to do the lab today. That's going to set up the equation that will eventually be able to answer that question down the line. All right, so we'll come back and revisit that question maybe next week, maybe. All right, so this is going to be Centripetal Force Lab. And now yesterday I showed you guys the setup a little bit, but go back, explain some things, show you guys how to fill out this table, hit some commonly asked questions. Okay? So you guys are going to have this type setup. I got a PVC pipe. I got a couple of Play-Doh canisters connected by a string going through the middle. And the Play-Doh canisters, so you can pop these open and you can put lab weights in it. This one's there's 50 grams inside this one. Oh, that restarted, right? So when I close this, it's 50 grams plus the canister itself, right? These canisters also have some mass. Let me find that mass paper. Here it is right here, right? So guys, here's the canister information. So these little tiny canisters, let's call these 6 grams each. And I wrote that right here. See a small canister, 6 grams? If you get a standard size Play-Doh canister, I'll call that a large canister. Let's call that 11 grams. Those are really close. Those are plenty close enough to get good data, and the graph's going to end up okay, pretty good at the end. Okay, all right. So you guys get that? Now add those masses to whatever you put on the inside. So let's see if you guys follow. If I have this 100-gram mass, guys, this is 100 grams, and I pop it inside a 6-gram canister, then what's that total mass right there? 106, right? You just add it up, right? I wasn't able to get hold of a scale, but we can just add the masses and it'll be all good like that. Okay. All right, so here, I'm gonna wheel this around in a circle, just like this diagram shows. Maybe zoom out a little bit, see it a little better, right? And see if I do this right, I can keep a constant radial size, and okay, and everything's just kind of in place, right? Like this bottom canister is not moving up or down. Now, this top one is on a curved path with a constant radial size. Okay, that's it, right? Let's talk about equilibrium. It's this bottom one that's not moving at all. It's not moving up. It's not moving down. Is it in static equilibrium? Yeah, it is in static equilibrium. These two forces, the weight down and the tension force up, are canceling out. It's in true static equilibrium. What about the swinging mass up here that's on a curved path? Is that in static equilibrium? Okay, is anything on a curved path in static equilibrium? No. What does Newton's first law of motion say? Newton's first law of motion, if anything is moving, it wants to move in a what kind of path? Straight line, right? So anything that's on a curved path, there has to be an external force. In this case, it's provided by the tension, and that's acting as the centripetal force. And you guys are gonna figure out what an equation that's gonna link all these variables together, right? Do you guys see this tension is exactly equal to this hanging weight? Ah, right, you guys see that? So whatever the hanging weight is equal to the tension, is acting as the centripetal force. That's holding the swinging mass in place. Right. And this path that's on, this curved path has some radial size. So maybe that could be a variable. That's how many variables so far? Got the hanging weight, that's one. Got the swinging mass, that's one. Got the radius, that's one. So it's up to 3. 1, 2, 3. Okay. And then there's going to be some tangential velocity, or I might just call it a speed, to keep everything in check. That could be a fourth variable. You guys see 4 variables there? Oops, got my equation out here. So cover that up a little bit. You guys aren't supposed to see the equation yet. Right? You guys going to derive the equation from experimental data. But you guys see 4 variables, right? I'm not counting the tension that's internal to the system. Also, the tension is just equal to this weight anyway. So that's 1, 2, 3, 4 different variables. You guys see that? And so to make any sense of this, I'm going to have to put you guys in 3 different experimental groups. And there should be a card on your desk with a suit on it. That's going to tell you what group you're going to be in. But getting a little bit ahead of myself. Before I get to that, let's look at this lab table. Okay, lab table. Now, your guys' lab table is ever so slightly different than this one. It's almost exactly the same, but a couple of different changes. Right. So what trial 1, 2, 3, 4, 5. Right. You guys got that. Right. Now, on your table, I did not put a column for gravity field. But do you guys know what is the gravity field of Earth? Yeah, 9.8 meters per second squared, or 10 meters per second squared. Pick your favorite. Right. So you guys, maybe you could write that out in the margin or something. Right. That's going to be useful here pretty soon. I do have a column for mass hanging. Now, on the big one, I put kilograms, but on your lab table, I went ahead and did grams. Guys, what is 1 gram compared to 1 kilogram? It's a factor of 1 over a what? 1,000. Yeah, it's 1/1000. 1 gram is 1,000th of a kilogram. If this was a textbook question, all the numbers should probably be in kilograms. But for your lab, let's go ahead and do grams. Now, guys, how do you go from the hanging mass to a hanging weight? How do you go from mass to weight? You just multiply by the gravity field, right? Now, if your mass is in grams and not kilograms, it's off by 1 over 1,000. You're going to get a weight that's not in newtons, but in millinewtons. That'd be true, right? So, guys, for example, suppose you had suppose you have this canister, 6 grams. Let's say it's empty; it's just 6 grams. You guys could put 6 grams for the. Actually, you know what? Probably the hanging one you want to be heavy. Does that make sense? You want the hanging one to be heavy? Let's change that to, let's say you put in 100 grams inside it. So that brings it up to 106. Is that okay? So 106 grams could be the hanging mass. I'm just making something up. Maybe you could do something a little different. Guys, 106 grams weighs how many millinewtons? What's 106 times 10? 1,060? Ah, right. Or you could do times 9.8 if you wanted. Okay, it'd be about 1,000 and something, right? Right. Okay, I don't care about the hanging mass. I care about the hanging weight. Right. Okay, let me go back to this diagram and remind you guys why. Right. There's 2 different canisters. The one that's swinging, I care about the mass. The one that's hanging, I care about the weight, because that's a force. Weight is a type of force, right? Right. And on your own lab table, I went ahead and made that bold as one of the variables that matters. Right. And so moving on. Okay, so hanging weight, that's a force. That's right there. The mass that's swinging. Hey, now you just get the mass of the swinging canister. And that's all you care about, the mass. On your own lab table, I put that in grams. Right. Next column, 1 over the mass. Go ahead and do the calculation. You guys can just calculate. Just put that in the calculator. Okay. Now, guys, when I say mass out of context, which mass am I talking about? The one that's hanging or the one that's swinging? The one that's swinging, because that's the mass you care about. The one that's hanging, you really care about the weight. The one swinging, you care about the mass. Okay, so 1 over the mass is what swinging mass. Right. Next column, radius. Now I did go ahead and put the radius in meters on, also on your own lab table. So for example, guys, suppose you locked in the radius at 50 centimeters. I'm just making something up. 50 centimeters. How many meters is that equal to? 50 centimeters. How many meters is that? 0.5. Yeah, it's 2 decimal places. So 50 rolled 2 decimal places, that's 0.5 meters, half of a meter stick, right? I bet your radius values are going to be kind of in that ballpark. It's going to be 0.3, 0.5, 0.7, 0.9, maybe some other meters. Right. Now these last few columns have to do with trying to get this speed right here. Right. Now the speed, maybe you could take a speed gauge and put it up here, and the swing mass could go through the speed gauge. You could measure it directly that way, but that's really, really tricky. There's a more practical way to get the speed, this tangential velocity, the speed, and that's to calculate it. So, guys, what is speed? Speed is what divided by what? Distance over time, right? Like miles per hour, meters per second, distance over time, right? Okay. So let's think about what distance and what time. Okay, so if this goes around a circle, what is the distance around a circle called? Circumference, right? Hey, and if you just measured the radius, how do you get the circumference from the radius? Circumference equals 2 pi r. Okay, so if the radius was, again, for example, 0.5 meters, you can just multiply that by 2 pi, and that's the distance around. Is that true? Okay. And if only you had a stopwatch. Hey, you got a stopwatch. Now you can time how much time to go around. Say that distance divided by that time, boom, that's the speed. Is that true? Right. No, there's a little catch here. I've got a little bit more to say about that, though. Because here's the tricky thing. It's probably going to be less than a second to go around. Guys, do you think it's really hard to like start, stop, and you do like a fraction of a second like that and get that actually accurate? Right. But what if you do this? What if you let it go around 10 times and you time it for 10 revolutions? And then you go back and just divide that by 10. Whatever error that is, suppose you were off by like 1 second, which is not possible. Maybe you're like Samuel the Sloth, like, oh, I got off by a second, a whole second. If that also gets divided by 10, now that's hardly anything. Now you're back being really accurate. Is that? Here, I'll do a demo for you guys. So here, if you're watching this video, just imagine I'm going to do this and I'm going to time it. Maybe hold my meter stick up next to this. Right. So do an example. You guys ready to see an example? Suppose I got this. I got, oh, there's 0.3 meters right there. Isn't that a ruler about 0.3 meters? Right. So I get it ready with the stopwatch and go. Sorry, scratch that. Instead of saying go, I'm going to say 0. Okay, so I'm going to start counting at 0. Does that make sense? Right. Ready? And 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And when I say 10, you stop the stopwatch. So from 0 to 10, because when you say 0, it hasn't gone around yet because it's starting, right? Okay, that makes sense too? Right. Right. No, guys, this is one of those labs that if you're really meticulous about collecting the data accurately, especially keeping this radius constant while you're spinning it, then your numbers are going to be really good. Your graphs are going to look really nice, and it'll lead us straight to the equations, and it's all going to be like by the textbook, and it's all going to be great, right? On the other hand, guys, I've taught this class so many years. I've seen this over and over. If you are not very careful about collecting your data, especially if this radius is like getting small and big and it's like growing, it's like or something like that, then all your data is going to be off, and the graphs aren't going to look very good. Oh, here's another one that I see students miss all the time. Okay. Look, guys, look at this hanging weight right here. Do you guys see 2 forces on it? Tension up, weight down. Do I want to go grabbing onto this weight right here? Do I want to do this? I was thinking like grab onto this and like, well, look, it's super fast. Do I want to do that? Do I do that? No, because now my hand would be supplying an additional external force, and now all my numbers are going to be off. You want this weight to be naturally balanced by this tension, which is providing that centripetal force. Okay, so you're not going to grab on the bottom one, just let it go. All right. Okay. So now we got to talk about what teams you guys are in. You guys see a card on your desk, right? Before I move on to that, anybody got questions so far? Everything makes sense so far? Look at the card on your desk. It has a suit on it. Let me make sure these are all going to be covered because I need to split you guys into 3 experimental groups. So Show of hands. Who has spade? Who has a spade on their desk? Okay, you got spade. All right, I think you have a spade too. Right here, you can join their group. These spades. Who has diamonds? Diamonds. Who has clubs? Right, and who has hearts? Okay, okay. So I have hearts marked as the wild card, just any of the above. So we're going to change out the hearts. Okay. So I think we definitely got spades covered. Definitely got spades covered. We need to cover diamonds. We need to cover clubs. Right. So you have clubs. Right. So okay. Somebody join Isabel and be clubs. Okay, because we definitely need clubs covered. Right. And the other one we need is diamonds. Who wants to switch to diamonds? Okay. So diamonds. Okay. Just make sure that the spades, the diamonds, and the clubs. I just need those 3 experiments covered, and then we'll be able to make all the graphs. Okay. Right. So what are each one of these? Right. So guys, remember there's 4 variables floating around. This M, this weight, F for force per weight, this R radius, and this V like tangential velocity speed. 4 variables. So depending on which seat you have, you're controlling 2 of those 4 variables. You're having one is independent and one is dependent. By the way, no matter which card you have, everybody has as their dependent variable is going to be the speed. Okay, so speed's dependent variable for everybody. Okay. All right, so let's start with the spades. If you have the spades, here's what you're doing. You're going to control the hanging weight, which is to say this bottom canister, you're going to leave sealed the entire class. Make it pretty heavy and it's just get locked all class. You're also going to control this radial size. Suppose you lock in at 50 centimeters, call it 0.5 meters. That'll be the same all day today. That's if you have the spades. What you're changing with the spades is this swinging mass. So you can open up this canister, you can pop in different lab weights, and then maybe I cross this over, seal that, boom, and then I'll stay locked in place right there. Something like that. Right. So that's it. Okay, you guys go with the spades. You guys know what you're controlling and what you're changing. Right. Right. And then again, there's gonna be some natural speed that sets up. Hey, let's do a quick hypothesis. Let's do a hypothesis for the spades. Let's say as you change the swinging mass, if you make it heavier and heavier, should you have to spin it faster or slower? Let me see a show of hands. How many of you guys think with the heavier swinging mass, you're going to have to swing it faster? Who says faster? Who says with the heavier swinging mass, you have to swing it slower? Okay, so I'm seeing hands on both of those. Right, so somebody's right. Right? And whichever one's right, you can go an extra step and say, how exactly are you right? Is it a square or a square root relationship or an invert? So we'll figure that all out on Friday. Let's move on to diamonds. If you have the diamonds, you're going to leave the top canister sealed, and also the radius is going to be locked in place. Right? But you're changing the hanging weight. So the other canister. So if you have the diamonds, you're changing out the bottom canister all class. You guys got that? Right? Let's do a quick hypothesis. So as you make this hanging weight heavier and heavier, what happens to the speed? A heavier weight, do you have to swing this faster or slower? Show of hands. Who says faster? Faster with a heavier weight. Who says slower with a heavier weight? Okay, so I'm seeing votes on each one of those. So if somebody's right, we're going to know by Friday. Right? Finally, the clubs. Now, if you have the clubs, you're going to leave both Play-Doh canisters sealed the entire class. Which we'll be changing is this radial size. So maybe you could start kind of small, like 30 centimeters, and then move up to 50 centimeters, and then 70 centimeters, and then 90 centimeters. So your radius is your independent variable, right? Now, guys, as this radius is getting bigger, 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 what should be the corresponding speed, faster or slower? All right, so show hands. How many guys think with a larger radius, you'll have to be swinging it faster? Who says that? Who says with a larger radius, you're going to have to actually swing it slower? Who says that? Okay, so again, I'm seeing some hands on both of those. So if somebody's right, we're going to know by Friday, right? So that should cover all the card suits and all the experiments that you guys are doing, right? All right, so I think you guys are ready to go. You guys ready? All right, everything you need is back in the lab area. Get all your data today. Tomorrow, of course, we'll be in the media center, and then on Friday we'll put all the graphs together. Oh, I'll throw this up here too. The mass of the canisters: 6 grams, 11 grams. All right, you are set.